Today, we are diving into one of the biggest environmental puzzles of our time, plastic waste. But we're not just going to stare at the problem. Nope, we are exploring a wild new solution that's cooking up in science labs right now. Enzymes that have been bioengineered to literally eat plastic. Sounds like something out of a movie, right? Well, it's real and it's happening.
To really get a grip on the scale of what we're up against, just look at that number. 82 million metric tons. That's how much of just one single type of plastic, PET, we churn out every single year. You know, the stuff in our water bottles, our food containers, even our clothes. And almost all of it is designed to last forever.
All right, so here's our game plan. First, we'll get into why plastic is so incredibly tough to break down. Then, we'll look at a shocking discovery from nature that gave us our first big clue. After that, we'll see why nature's solution had some serious flaws, which leads us to the really cool part, the brilliant science of engineering a super enzyme. And finally, we'll ask the big question, what does all this mean for a truly circular plastic economy?
Okay, let's kick things off with part one, the unbreakable plastic problem. We're about to see why PET is, at the same time, this miracle material and a total environmental nightmare.
So the very thing that makes PET so great for us is also what makes it so terrible for the planet. It's a polymer, which is just a super long chain of molecules. Think of it like a brick wall. The building blocks are two chemicals, terephthalic acid and ethylene glycol. But the mortar holding them together, these incredibly strong chemical bonds. It's built for durability, for stability, and that's exactly why it just sits there for hundreds of years.
So how do we deal with it now? Well, the old school ways, physical and chemical recycling, are pretty much brute force. They take a ton of energy, they can spit out nasty byproducts, and a lot of the time, you get what's called downcycling. The plastic just gets weaker and less useful every time. But biological recycling? That's a whole different ballgame. It's elegant. It's about using nature's own tiny machines, enzymes, to break the plastic back down into its pure original building blocks, all at low energy. It's the green dream.
And that dream got a whole lot more real because of our next chapter, Nature's Accidental Solution. This is the moment scientists realized that this wasn't just a theory. It was already happening out there in the world.
Get this. Back in 2016, a team of researchers in Japan found something incredible at a plastic recycling facility, a tiny bacterium, Ideonella sakaiensis, that had actually evolved to eat plastic. It was producing this unique enzyme, which they called PETase, that could slice through PET's tough chemical bonds. It was a massive discovery, but, nature's first draft is rarely perfect.
So how does it pull this off? It's actually a pretty neat two-step dance. First, PETase comes in like the first pair of molecular scissors, and it snips the long PET chain into a smaller piece called MHET. Then, a second enzyme, MHETase, acts as the second pair of scissors. It chops up that MHET, releasing the original valuable building blocks.
Boom, simple as that.
So, we found our hero, right? Well, not so fast. Our hero enzyme had some pretty serious flaws. And that's what this section is all about, why this amazing natural discovery just wasn't ready for the big leagues.
Yeah, there were 4 big hurdles. First, it was just too slow, way too slow for any practical use. Second, it was fragile. It couldn't handle the heat, losing its punch about 40 degrees Celsius, which is a non-starter for industry. Third, it actually got in its own way. The MHET stuff it created would literally clog up the enzyme and slow the whole process down. And finally, it was a picky eater. It really struggled with the tough, super dense plastic that most of our bottles are made of. And that last point, the pickiness, that was the real kicker. As the researchers themselves put it, the degradation of highly crystalline regions of PET remains a challenge. If they couldn't solve that, this whole idea was basically dead in the water for real-world applications.
But this is where the story gets really, really cool. This is where we get to engineering a super enzyme. If nature gave us the rough draft, this is where scientists grabbed their red pens and started making some brilliant edits.
So, that led to the first big puzzle for engineers to solve. How do you get rid of that bottleneck, that traffic jam caused by the byproduct? How do you make those two enzymes work together like a perfectly coordinated pit crew?
And the answer was just ingenious. They decided to build what's called a whole-cell biocatalyst.
Basically, they took regular old baker's yeast and turned it into a microscopic factory. They engineered it to wear the enzymes on its surface like a jacket. But here's the magic trick. They added a protein scaffold, kind of like a molecular tool belt, that holds both enzymes right next to each other, ready to go.
And the difference was, well, it was huge. When you just have PETase working alone, you get a little bit of the final product. But when you put both enzymes on that yeast's tool belt, the second enzyme immediately snags the byproduct from the first one, clearing the way. There's no traffic jam. The whole assembly line goes into overdrive, and the output of the final product just skyrockets. That's synergy, right there.
Okay, so the teamwork problem solved. But what about the other big one, the pickiness? See, the surface of PET plastic repels water, and so does the yeast cell. So the little factory couldn't even get a good grip on its food, especially that tough, dense plastic. So how do you solve a stickiness problem?
You give it some molecular Velcro. Seriously, scientists engineered the yeast to display a third protein on its surface, right next to the PETase enzyme. This protein, called a hydrophobin, comes from fungi, and it has this incredibly powerful natural grip on water-repelling surfaces, like plastic. It basically makes the whole yeast cell sticky, so it can latch on tight to the plastic and get to work.
And here it is, the wow number. Adding that molecular Velcro boosted the degradation rate of that really tough, high crystallinity PET by a factor of 328.8. Let me say that again. Over 300 times faster. That's not just an improvement. That is a total game changer.
And you could literally see the difference. The researchers described seeing apparent cracks and erosion on the PET surface when they used their new system. Under the microscope, you can see these little engineered yeast cells just chewing pits into the plastic. Meanwhile, the original enzyme barely left a scratch. It's just incredible proof of what happens when you help the enzyme stick to its lunch.
So what does all this add up to? Let's take a step back and look at what these breakthroughs could really mean for the future of all this plastic.
This really puts the whole journey into perspective. In 18 hours, the original natural enzyme barely made a dent in that tough plastic, less than 1/100%. But the new system, with the teamwork and the molecular Velcro, it converted over 3% of that same exact plastic. And on the easier-to-digest stuff, a whopping 55% conversion. We are not talking about small incremental gains anymore. This is a quantum leap.
So, let's just quickly recap the main takeaways. At its heart, the plastic problem is a chemistry problem. It's all about breaking strong bonds. Nature handed us the first clue, the first tool, but it needed some serious upgrades. Then, through some absolutely brilliant bioengineering, scientists built a super-enzyme by solving its two biggest weaknesses, teamwork and stickiness. And these advances are a massive leap towards the Holy Grail, a truly closed-loop system where we can recycle plastic forever.
Which leaves us with one final massive question. We started this journey looking at a global mountain of plastic trash. We're ending it with a microscopic engineered microbe that can eat it. Now, we're still in the early days for sure, but it's impossible not to wonder, could these tiny living factories be the key to finally creating a truly circular plastic economy? Thanks for joining us.